Hello, student. I do this session to recorrect some mistakes I have done in tutorial 3 recorded session, which is related with the phase modulated signal, one example. So when we are calculating instantaneous frequency, we did some few mistakes. Okay, so this in this session, we hope to recorrect those errors. So actually, one of our student has shown the mistakes there. So I would like to thank her at this moment. So anyway, we will start. Okay, so so if we have a quick recap, you know what is phase modulation. The carrier signal phase is changing according to the message signal. Okay. So that is we called as phase modulation. Okay, so you already know that normally we are using sinusoidal signal with high frequency as a RF signal, carrier signal. Okay, so like this. So this is our carrier signal, and this is our carrier frequency, angular frequency, and this is our carrier amplitude, and this is the phase of the carrier signal. And you know, in phase modulation, we are changing this phase. No? We are changing this phase according to the message signal. Let's say it is XT. Our message signal is XT. Okay, so you know that this phi is not a constant, it is varying with time according to this message signal. So it is become a time varying function. No, it is a function of time. This phi will become a function of time. So this phi is changing according to the time, with respect to the message signal. Okay, so that is the idea of phase modulation. And you know the equation. Yeah, so we can define this phi t, this phase. Okay, so this is the phase phi t as phi delta xt. This is nominalized. No, we call this nominalized t. So you know that this phi is a phase modulation index. Okay, and normally the phase modulation index should be equal to 180 degree or 5 radian. Okay, so this xn is we call nominalized frequency. This xn, what is nominalized means, if our message signal is xt and the message signal maximum amplitude is a max, if we get the ratio x, if we divide this xt, our message signal from the maximum amplitude of that message signal, we have the nominalized message signal. Okay, so this is the nominalized signal. So here we are using the nominalized signal. Okay, so we can also write this as phi t as phi delta. So this is a nominalized one. Okay, so if I write the nominalized signal like this, okay, xt a max. Okay, so this is not a nominalized signal, it is a normal signal. No, it is a direct message signal. So if we consider this part, okay, we called it I think you can remember, we put it as kp, another constant, so we can use the direct message here, xt, like this. Okay, so we can finally write our modulated signal as AC cos omega ct plus Instead of 5t, we can put kp xt. Okay. And of course, we can write this xpm, the modulated signal, as cos omega ct plus 5 delta, but it is a nominalized signal, xnt, nominalized signal. Okay. It is not a direct message signal. This is a nominalized signal. That means message signal is divided with its maximum amplitude. Okay. So, so these are the basic things. Okay. So, so let's consider one specific time, T1. Okay, let's take T1. Okay. So at T1, so you can see that, okay, you can see that this is the angle of the complete signal. No, this is the angle of the complete signal. Let's say it is theta. Okay, and you can see that angle is varying with time. No, angle is varying with time. This theta is varying with time. So it is a function of a time somehow. No, okay. So so this is the angle of the complete signal, complete modulated signal, this one, and it has two parts. No, this is one part, this is one part, it carrier part, carrier frequency part, and this is another part, the message signal part. No, okay. So if we draw the phasor diagram, so we have drawn these things. Okay, if we draw the phasor diagram, okay, if we draw the phasor diagram at t is equal t, at t is equal to t1. So normally we are in phasor diagram, we mark the angle, no, angle here. We have to draw the angle here. So you can see that angle is consist with two parts. Okay, this omega ct and so delta 5 xnt or kp xt. Okay, we will use this one as usual. Okay, so so it is like this. Okay, this is our carrier signal part angle. Okay, and we have another angle. Okay, like this. It is this part kp xt. This is t1, no, omega c t1, and this is x t1. Okay, so this is the theta, the total angle at this time. Okay, at t1, this will be the total angle, and it consists of two parts, omega c t1 and kp x t1. Okay, so both part is there, both parts are there. Okay, so you can see that this theta is varying according to the time. No? This theta is varying according to the time, and this theta is also varying according to the message signal. Okay. So, so we can, if we plot the theta with respect to time, okay, if we plot the theta with respect to time, okay, we don't know, it will have some values, no, like this. Okay, we don't know the variation. So this variation this variation also depend on our message signal xt, no, message signal xt. Okay, so so now if you want to find this total angle at some point, okay, let's say it is t1. Okay, t1. So you can so you have this this is the angle, no, this is the angle. Okay, so theta, let's say it is theta t because it is varying with time. Theta t is equal to omega ct plus kp xt. Okay, so this is the angle. Okay, so at t is equal to t1, okay, we can find that instantaneous angle. Okay, that means the angle at this point. Okay, at T1. So we can write it as omega c T1 plus Kp x T1. Okay, so this is the instantaneous angle, the total angle. Okay, and so normally this is the total angle, and this part is considered as the phase. Okay, this part is considered as the phase of the signal. Okay, this part normally referred as a phase, as the phase of this complete signal. Okay, so if you want to calculate the instantaneous phase at t is equal to t1, if you want to calculate the instantaneous phase, okay, instantaneous phase, so it is, let's say it is 5t. Okay, so 5t is equal to kp xt. Okay, so if you want to find the instantaneous phase at t1, that means 5t1 is equal to kp x t1. Okay, so you can directly find the instantaneous phase there. Okay, so in some books, sometimes this total term is referred as the phase. Okay, in some books, this total part is referred as the phase. Okay, but according to our reference book, the phase is referred to only this part. Okay, only this part, only for this part. Okay, that means phase is instantaneous phase. You can write this x phi delta nominalized signal, or you can write this phi t as kp our message signal, like this. Okay, so this is the instantaneous phase. Okay, and here we have the instantaneous total angle. Okay, so this is total angle theta. Okay, so this theta is total angle, and this phi is the phase. Okay, I will write it here again. Okay, so if you want to find the total angle theta, then it is equal to omega ct plus kpxt. So this part you can write as 5 delta x nominalized t, like this. Okay, so so this is the total angle. Okay, and the phase is 5t is equal to kpxt. Okay, so you can write this as 5 delta nominalized xt. Okay, so both are correct. Okay, so this is instantaneous phase. Instantaneous phase. Okay, so you can see that this theta is varying with time, but it is not a constant. No, the variation is not constant. Okay, it is randomly varying. Not actually, it is not randomly varying. It is varying according to this message signal. Okay, message signal. Okay, so say that you want to find the rate of change of this theta. Okay, so you want to find the rate of change of this theta at t1. Okay, so we want to find, okay, rate of change of this theta, total angle at t1. Okay, at some instant. Okay, so this is t1 is some instant, arbitrary instance. Okay, so you want to find the rate of change of this theta at some point. So how can you find it? Okay, so you normally know that if it is varying linearly, okay, so it is varying linearly, you can get the difference of theta and the time take to time that take to get this different, no? So you can find the the rate of change like this, okay? Delta t plus delta t. So this is the phase difference, angle difference, okay? And this is the time difference that take to get this angle difference, okay? But here it is very arbitrary, randomly, okay? Not randomly, it is arbitrary. So this is change is according, this change is relevant with this message signal, okay, xt, okay? So so what you have to do to find this variation? So you know that we can get a small theta deviation delta t, and you can get that small time duration delta t, okay? And you can limit this delta t, okay, this t into 0, no? This t into 0. So it is dt by d theta by dt, no? So derivation. So you know that at any point, so this is the basic of the the differentiation, no? This is the actually this is the definition of integration, the derivation, okay? So if you want to find the rate of any point, the the rate of change of any point, okay? So what you have to get? So you have to get the derivative simply, no? So you can get the derivation, okay? d phi d theta by dt, okay? Then you can find the change of rate, okay? So what is this range of the rate of change of this theta, okay? So if you get the derivation dt by dt d theta by dt, you can get the rate of change of this theta, okay? So what is the rate of change of this theta, okay? So that means theta is varying according to the time, okay? So some theta is changing and we have get some time, no? So what is this? It is the velocity, no? It is the angular velocity, omega, okay? So this is angular velocity, okay? So we can say that this is angular frequency also, okay? Angular frequency or angular velocity. So finally, if you want to, so you have this theta phi t, that is omega ct plus kp xt, okay? So if you want to find the rate of change of this theta, so what you have to do, you have to get the derivation, no? So this theta, so this is not phi, I'm sorry, okay? So this is theta, okay? So theta is equal to omega ct plus kp xt, okay? So this is theta. So if you want to get if you want to find the rate of change of this theta, then you have to get the derivation, no? So that is d theta t dt you have to get, and also you have to get the derivation from this side also, omega ct plus kp xt by dt, okay? So this is the rate of change of at some instant, no? Okay, so this rate of change actually angular frequency, no? It is an angular frequency at some point, no? At some specific point, specific instant, okay? So that is we can refer it as an instantaneous velocity, no? Instantaneous angular velocity, instantaneous angular velocity, So we can we can say that it is instantaneous angular frequency. Okay, angular frequency. Okay, so omega t angular frequency is equal to instantaneous angular frequency. So you can find the angular frequency at any instant, no, using this. Okay, so and the instantaneous angular velocity, you will have angular frequency, you will have the derivation of this. Okay, so omega ct is differentiated with dt. You will have omega c here, no? Okay, so the differentiation of t is equal to 1. Okay, t is equal to 1. Okay, so you have this constant only, omega c, and here you have kp, this derivation, no, this d, it's t dt, this derivation. Okay, so what is this? This is angular frequency of some instant, so that we can say that this is instantaneous angular frequency. Okay, so this is instantaneous angular frequency. And if you want to find the normal frequency, okay, so omega is angular frequency. If you want to find the normal frequency, you know that, okay, 25f is equal to omega, no? Okay, 25f is equal to omega. We know this. Okay, so you can for this and for this position, okay, for these terms, you can simply apply this term, no, 25f. So here, this omega t, we can write as 25ft. So this is the instantaneous frequency. Okay, so ft is instantaneous frequency. Okay, and it is equal to this omega c, and it is equal to 25fc. So this fc is the carrier signal frequency, 25fc plus kp d xt by dt, like this, no? Okay, so if you divide these all terms by 25, okay, 25, then you will get ft is equal to fc. Okay, this 25 cancel out. Okay, and here you have kp by 25 d xt et. Okay, so this is the angular frequency. Okay, so sorry, instantaneous frequency. So this is the instantaneous frequency of phase modulated signal. Okay, so in my when we are doing that example, I just forget this derivation. Okay, I just forget this derivation and this 25. Okay, then at my, so this is the correct one. Okay, so this is the correct one. So this is the correct one. Okay, but when I was doing the example, I take this ft as fc plus kp xt. Okay, and I have forgot this 25 and this derivation. Okay, so at that time it is a mistake. Okay, so this is the correct way. Okay, so if you have xt as cos as am cos omega mt or like this, so you have to get the derivation here. Okay, dxt dt first. Okay, then you have am sine omega mt by omega m. Okay, so this is the derivation. Then when you are finding the instantaneous frequency, you have to use this derivation. Okay, so you can write any instantaneous frequency at T1 or something using FC plus KP to 5. So this is the derivation AM sine omega mt. Okay, and here also omega m is also there. Okay, sine omega m T1. So you have to use this. You have to use this kind of expression to evaluate the instantaneous frequency. Okay, I hope you get it. So please do it correctly. Okay, so in our example, this FC is given, this KP is given, and this AM cos omega m t also given. So you have to just apply the value here. Okay, then you can write it. Okay, so I hope you can do this. Okay, so this is our reference book. Okay, so you can see that this is the phase modulated signal. Okay, so this 5, it is the phase of the signal and it is changing with time. Okay, so so this is total angle omega ct. This is total angle and it is equal to omega ct plus 5t. Okay, so this is the total angle, and you can find any instantaneous angle using this expression. Okay, no issue. Okay, and this is the exponentially representation with only real parts. Okay, and this is the definition of 5t delta 5 by xt, and this is the condition. Okay, actually this condition, we apply this condition to have physical difference between the angles, no? Between this 5t different angle, we need physical difference between angle. So that is why we use we keep this delta 5 delta with this range. Okay, so we have discussed these things, so I think no need to discuss it again. Okay, and here you can see we get the rate of change. Okay, that means we have to get the derivation, so that is why here put dot mark here. That represent the derivation. So here also we have to get the derivation. That is why this 5 dot t is there. Okay, so this that dot mark. Okay, like this. Okay, so finally we will have this result. Okay, so this is our instantaneous frequency phase, and this is our instantaneous frequency. So we have to get the derivation, this x dot t here, that represent the derivation. Okay, so I hope you got the idea. Okay, I am sorry for my mistake again. Okay, and thank you.